Hello, in this video, we're going to continue our work with solving linear quadratic systems. But instead of solving them graphically, we're going to be solving them algebraically. I'm going to be using my pen tool. This may be a little bit challenging without a virtual pen. I do have my pencil. I'm using purple, and I have the sizer all the way down. I'm noticing that both of these equations are set equal to y. Therefore, since they're both set as equal to y, I can set this equal to that, right? Because they both equal y. So I'm going to go back to my pencil tool, and I'm going to say that x plus 2 quantity squared minus 6 is equal to 4x minus 2. Now I can see that I have a quadratic expression here, or a binomial, which I need to square. To square that, I'm going to use the box. I know that many of you prefer the box. So we're going to do x plus 2 times x plus 2, giving me x squared plus 2x. Here's a 2x and there's a 4. So my quadratic term is x squared. My linear term is 4x. They don't cancel, be careful. And my constant term is 4. So I have just squared this binomial, and this is the trinomial that I got. I'm going to subtract 6, like the equation says, and set it equal to 4x minus 2. Now what I want is all of my terms on the left and a 0 on the right. So I'm going to subtract off a 4x, and I'm noticing that there's a 4x over there. So they just cancel each other out. The constant terms here combine together to equal -2, but there's a -2 on that side, so they would cancel out. Okay, leaving me with the following quadratic equation, the simplest of all quadratic equations, x squared equals 0. So I can go ahead and take the square root of both sides, and when I do, although I typically get plus or minus, in the case of 0, there's only one solution. So there are not two solutions, there's one. The x value of that solution is 0. And to get the y value, I can substitute 0 in place of either equation because 0 satisfies both of them. It's the solution. I'm going to pick the linear equation. I'm going to do y equals 4 times 0 minus 2. Y equals 0 minus 2. Y equals -2. So I have my solution of that linear quadratic system. The solution is 0, -2. If you go back a few slides, this was the example that we could see the one solution on the graph, but it looked like there might be another solution and we just couldn't zoom in enough, even with Desmos. Now, algebraically, I have confidence in stating there is one solution. All right, so I'm going to move on and try another example here, okay? All right, I have a linear function and I have a quadratic equation. And I'm going to set my quadratic equation equal to my linear because I want to know where are the x values the same. I'm going to add 5 to both sides. And I'm going to try to do backwards FOIL for this trinomial. And I'm thinking, what times what equals x squared? Well, that would be x. I'm thinking, what times what equals 2? Well, the only thing I could do is +2 and +1. But then I see, wait, I want my middle term to be negative. So I have to make both of these negative. So I'm going to try this again. I'm going to try x minus 2 times x minus 1. And I'm thinking this is right, but when I check FOIL, FOIL, and I do the first two, no problem, that checks out as x squared. My outside, -1x, and my inside, -2x, does not together equal this middle term. So I'm getting to this place where I'm understanding that this particular trinomial cannot be factored. So if it can't be factored, my next approach is, okay, how about the quadratic formula? All right, so I'll do that next. The quadratic formula, you'll recall, negative b plus or minus the square root, so x equals negative b plus or minus the square root of b squared minus 4ac all over 2a. And the a, the b, and the c that I'm using are right here. A equals 1, b equals negative 2, c equals 2. I'm going to plug those right into this quadratic formula. I'm actually going to erase a few things that I have here. And instead of anywhere I see b, I'm going to put the value of b. So I'm going to start with that. So b is negative 2. So this is the opposite of negative 2, plus or minus negative 2 squared minus 4 times a times c. Okay, where's my eraser? I'm going to change a. Every time I see a, I'm going to put a 1. And when I see the c, I'm going to put a 2. And now I'm going to simplify this expression. And when I do, something interesting happens here. I end up realizing that I'm going to have complex, I have a negative discriminant. Let's look. The opposite of negative 2 is 2, plus or minus the square root of 4 minus 8. That's negative 4, all over 2. Now, while there is an imaginary number that is the square root of negative 4, right? And we know that it's 2i. This doesn't make sense with the context of what I'm talking about. I'm talking about the coordinates x comma y where these two functions would intersect. And you cannot use complex numbers or imaginary numbers, even though I can simplify this to 1 plus or minus I. This does not work on the coordinate plane. And so if I were to graph this on Desmos, this parabola, this linear function will not intersect. And I will show you that, okay? Here's my quadratic function. It was y equals x squared minus 2x minus 3. And here's my linear function down here. There is no solution. And how we interpret that in the realm of an algebraic solution is when you end up with not real values of x. So we can simply write there are no real solutions. And that's what we're interested in when we're talking about linear quadratic systems. I will try another example, okay? All right, here's my next example. Because they both equal y, I'm going to set them equal to each other. I'm going to say negative x squared minus 2x plus 7 equals negative 2x plus 2. Now I'm going to bring the negative 2, oh, look at negative 2x on both sides. You know what that means. That means like they can eliminate. But I am going to subtract 2 from both sides. So I get negative x squared plus 5 is equal to 0. Now watch this. This is interesting. How about if we subtract 5 from both sides? Don't take the square root until you get the x squared by itself. Let's divide both sides by negative 1. Now let's take the square root of both sides. And I get that x is equal to plus or minus the square root of 5. That is a real number. It's not the square root of a negative. That's simply an irrational number. So what I do is I take this x value and I substitute it into either equation. I always pick the linear because it's easier. And I'm going to say negative 2 times positive square root of 5 plus 2. That's negative 2 root 5 plus 2. That's my y value. So I have one solution here at root 5, negative 2 root 5 plus 2. And doesn't that look strange as an x comma y coordinate? And remember yesterday when we looked at this system, they were irrational numbers. They were weird looking decimals on the Desmos graph. Now I know why, because these are irrational numbers at which these graphs are intersecting. My other solution is the negative square root of 5. And then we have negative 2 times negative root 5, which is 2 root 5 plus 2. Those are my two solutions. And how I'm just going to end this video is just showing you this one. I'm going to type these into Desmos so that you can see how to interpret these strange looking solutions. Here's the linear. Y equals negative 2x plus 2. There's your linear function. Let's make it in red. Okay, my quadratic function, negative x squared minus 2x plus 7. I like my quadratic function in blue. And I can see that there are two real solutions, okay, because this is the real coordinate plane. And so the solutions, the coordinates here, are irrational numbers. And we mentioned that yesterday. We mentioned that these coordinates look like they're probably irrational. Now we have verified that this square root of 5 is rounding to 2 times, or 2.236. If I do Desmos scientific calculator, just to make even more sense of this, and I say, what is the square root of 5 approximately? Because that's my x coordinate, right, everybody? Square root of 5. I go square root of 5. There's that 2.236 that I see on Desmos. Same thing with negative square root of 5. All right, that's a little background on solving linear quadratic systems algebraically.